So in this question, we have to identify the compounds with the structure related to the diglyceraldehyde. First of all, you have to draw the structure of diglyceraldehyde. So here it is CHO, at the bottom CH2OH, right hand side you have OH, left hand side you have H. This is the Fischer production of diglyceraldehyde. If any structure looks like the diglyceraldehyde, that means at the last chiral center, if you have the OH group at the right hand side, then it is said to be a diglyceraldehyde. So here it is the last chiral center, OH we have at the right hand side. So it is similar to that of diglyceraldehyde. A is correct. Here it is the last chiral center, OH is present at the right hand side. It is also a diglyceraldehyde. It is the last chiral center, OH is present at the left hand side. That's why it is L-glyceraldehyde. C is not correct. This one, the most oxidizable group CHO is present at the bottom. You have to take that most oxidizable group to the top. So rotate this molecule by 180 degrees. Then you can get CHO here. And you can get OH to the right side. And the last chiral center here it is. OH is getting right hand side. And OH here we are getting to this side and OH we are getting to this side. So for the last chiral center, OH is present at the right hand side. That's why it is also a diglyceraldehyde. D is also having correlated to the diglyceraldehyde. So A, B, D, 3 are having diglyceraldehyde similar structures. So 3 is there on option 1, which is the correct answer for the given question. When secondary butyl cyclohexane react with the bromine in the presence of sunlight, the major product obtained is. What is meant by secondary butyl group means if I am going to take butane, here one hydrogen is there. If you are removing this secondary hydrogen from the butane, you can get the secondary butyl group. And this secondary butyl group which is attached to the cyclohexane, then you can get the compound cyclohexane. And here it is secondary butyl group which is called a secondary butyl cyclohexane, which is reacting with bromine in the presence of sunlight. So the given reaction is a free radical substitution reaction. So the most free radical the most stable free radical obtained in this reaction is, for example, if I am going to write the free radical here and another combination, here it is the cyclohexane and here it is the secondary butyl group, and free radical I am going to give here. Both are tertiary free radicals, but this free radical is having 3 plus 2 plus 1, 6 hyperconjugated structures. This free radical 2 plus 2 plus 1, only 5 hyperconjugated structure. So this free radical is more stable. So that's why the hydrogen attached to this carbon is replaced by Br. You can get this particular product as a major product. So option 3 is the correct, not option 3. Option 4 is the correct answer for this question. So in this question, match the compounds in the list 1 with the appropriate catalyst or reagent of the list 2 for their reduction into their corresponding amines. So for example, here I am going to take RC double bond NH2, which is nothing but an amide. So this amide I am going to take RC double bond NH2. So this RC double bond NH2 on reacting with lithium aluminum hydride, a good reducing agent through hydride transfer, which when convert that particular amide into amine, corresponding amine, primary amine you can get here. So A is matched with 3. 3 is on lithium aluminum hydride. Now, if I am going to take the compound benzene which is connected to NO2, nitrobenzene, which is on reacting with tin in the presence of HCl, nitrobenzene undergoing reduction in the presence of acetic medium, then we can get aniline. So here it will be 4. And the next one, RCN. cyanide, Rc triple bond N, which is on reacting with H2 in the presence of nickel, catalytical reduction. Cyanides which is on reacting with the catalytical reduction, you can get the primary amine. So the primary amine here it is 4. So 4 is the, not 4, 2, cyanide for 2. And the next one, if I am going to take RC, not RC, benzene which is connected to C double bond O, C double bond O and H, it is a N-alkyl phthalimide which is on reacting with the water in the presence of NaOH, basic hydrolysis takes place, aqueous NaOH. So here you can get H, here also H, OH, OH. This is the part of Gabriel phthalimide synthesis. Then you can get benzene which is connected to COOH, COOH, which is called as phthalic acid plus RNH2, a primary amine you can prepare. So the suitable reagent for this one is 1. So A3, B4, C2, D1. Option 4 is the correct answer for this question. So here I am going to take an RBR which is on reacting with magnesium in the presence of dry ether. Alkyl bromide reacting with magnesium in the presence of dry ether, you can get RMGBr, alkyl magnesium bromide, which is a Grignard reagent, which is on reacting with the water, you can get RH, hydrocarbon. That hydrocarbon is given as isobutane. So how many different alkyl bromides that can react with the magnesium followed by hydrolysis gives this 2-methylbutane I am asking. It is isopentane, not isobutane. So for example, if I am going to take the compound, here I am going to take a Br. So which is on reacting with magnesium followed by hydrolysis, you can get this particular 2-methylbutane. And here you can take the Br. This one also can produce the same 2-methylbutane. And the next one, here it is the methyl group, here it is Br, which one can also produce this 2-methylbutane. And this one also can produce 2-methylbutane. And in this question clearly mentioned, we have only considered the structural isomers, no need to consider any stereoisomers. So 1, 2, 3, 4. These 4 alkyl bromides can give 2-methylbutane by reacting with magnesium followed by hydrolysis. So answer for this question is option 1. The most stable carbocation from the following is. So the carbocation will be stabilized very easily when it is connected to an electron donating group. That electron donating group that should exhibit positive mesomeric effect or positive inductive effects. So if I am going to taking this particular benzene, and here it will be CH2 plus benzyl carbocation, and para position is having O-methoxy group that is having 2 lone pairs and having plus M effect and minus A effect. Plus M is more dominated, that's why it is more stable carbocation. And the next one is benzene, and here it is attached to CH2 plus benzyl carbocation. Para position is having CH3, so which is having plus A effect and plus H, hyperconjugation. So no mesomeric effect, but mesomeric effect having more priority. That's why OMe connected benzyl carbocation is more stable when compared to methyl connected carbocation. And the next one, benzene, which is connected to CH2 plus benzyl carbocation, no electron withdrawing group is present, no electron donating group is present. That's why it is less stable when compared to paramethyl and paramethoxy. And the last one, benzyl carbocation, CH2 plus, which is having OMe group at the meta position. So with respect to this CH2 plus, OMe is at meta position, that's why it cannot exhibit any resonance. So plus M effect is not operated here, only minus effect is operated, which is the less stable carbocation. So most stable carbocation is option 1. So here it is the statement 1, statement 2 type of questions. In statement 1, nitrogen, sulfur, halogen, phosphorus present in the organic compound are detected by Lessons test. Yes. Lessons test is the extra element test. You can convert the given covalent bonds by treating with the sodium metal to ionic bonds. So you are going to treat with the sodium metal. In this extra element test, Lessons test, we can identify the nitrogen, sulfur, halogen, phosphorus. It is correct only. Statement 2, the elements present in the compound are converted from covalent to ionic, correct only, by fusing with the compound with magnesium. Magnesium is wrong. It is fused with sodium. That's what is called a sodium fusion extract. Statement 1 correct, statement 2 wrong. It is there on option 3, which is the correct answer for the given question. So the question given is toluene, which is on reacting with CrO2, Cl2, CS2. It is an Ettard reagent, and that reaction is called as Ettard reaction. So toluene on reacting with CrO2, Cl2, CS2 followed by hydrolysis. First oxidation takes place, followed by hydrolysis, then you can get benzaldehyde. This benzaldehyde, which is on reacting with sodium bisulfite, NaHSO3, Na plus and HSO3 minus. It is a nucleophilic substitution reaction, nucleophilic addition reaction. You can get O minus and that will be attached to Na plus. So here you can get benzene, which is connected to C and connected to O minus, Na plus, which is connected to H and connected to SO3H. Proton transfer takes place, hydrogen here and Na you can get here. Then the compound obtained is benzene, which is connected to C, connected to OH, connected to H, and which is connected to SO3 minus and Na plus. This is the filter and residue A, and which is on reacting with the HCl, which undergoes a hydrolysis. Then the carbon is having two OH groups, water eliminated. Then you can get benzene connected to CHO. Benzene connected to CHO. Benzaldehyde you can get. And the reaction of NaHCO3 with aldehydes used for the purification process also. So option 4 is the correct answer for this question. Option 4, A here it is, which is on reacting with HCl, you can get benzaldehyde. The alkane which below have the two secondary hydrogens are. Secondary hydrogens are nothing but the hydrogens which are connected to the secondary carbon are called as secondary hydrogens. So if I am going to take 2, 2, 3, 3 tetramethyl pentane, 1, 2, 3, 4, 5, 2, 2, 3, 3. So here it is the primary carbon, here it is the quaternary carbon, secondary carbon, it is the primary carbon. Secondary carbon is having the two hydrogens here, that's why it is having two secondary hydrogens. So option 3 is the correct answer for this question. The compound with the molecular formula C6H6, which give only one monobromo derivative and takes the 4 moles of hydrogens for the complete reduction, then the number of pi electrons are. So see here the structure, if I am going to take a triple bond, and here it is a triple bond like this, and here it is the again methyl group, which gives only one monobromo derivative. That one monobromo derivative is, so here you can get Br, and here it is a triple bond, and here also triple bond. So which is having 1, 2, 3, 4 pi bonds. 4 pi bonds are having 4 hydrogen molecules for the complete reduction. So 4 pi bonds means 4 2s are 8 pi electrons it is having. So answer for this question is H. So it is having molecular formula C6H6 also. It produces only one monobromo derivative and having 4 pi bonds.